Professor Rao completed his BSc and MSc in Statistics from Andhra University and Usmania University, respectively. PhD in Statistics and MTech Computer Science Engineering from Usmania University. He started his career as a lecturer in statistics at Usmania University, Hyderabad in 1984. Since 1986, he is working in the University of Hyderabad. He worked as a dean in charge of the School of Mathematics and Statistics, University of Hyderabad, from 18th December 2019 to 20th July 2020. Presently, he is a senior professor in the School of Computer and Information Science, University of Hyderabad. His current research interests are simulation and modeling, rough sets, and knowledge discovery. Dr. Rao is a member of the Operation Research Society of India, Indian Mathematical Society, International Association of Engineers, Society for Development of Statistics, Andhra Pradesh Society for Mathematical Sciences, Indian Society for Probability and Statistics, Society for High Energy Materials, International Rough Set Society, Indian Society for Rough Sets. He was the founder secretary of Indian Society for Rough Sets and also a fellow of the Institution of Electronics and Telecommunication Engineers, Society for Sciences and Andhra Pradesh Academy of Sciences. He is a senior elected member for International Rough Set Society 2016. He received Lifetime Achievement Award, Acharya Ratna, on 2nd October 2019, 150th birthday of Father of the Nation, Mahatma Gandhi, by Indian Services in association with APITA, TITA, Lions Club, Takshashila IAS Academy, and Impact. Dr. Rao guided 15 PhDs, 62 MTechs, 8 MPhils, nearly 83 journal and 122 proceeding papers, and 1 Australian innovation patent to his credit. He published several books, which includes Evaluation of Total Literacy Campaign, co-authored with Professor B. Krishnamurthy and Dr. L. Ramabrahmam, and another book, Multidisciplinary Trends in Artificial Intelligence, 8th International Workshop, MIWI 2014, Bangalore, and another one is Strategic Polysymmetric Search for Web Mining, co-authored by Dr. K. Himabindu, published by Lombard Publications. Another book is Coefficient of Variation and Machine Learning Applications, co-authored with Dr. K. Himabindu, Dr. Raghava M, and Dr. Nilanjan De, by CRC Press. Another book, Advances in Computational Intelligence and Informatics, Proceedings of ICACII 2019, co-editors Distinfansu Salvatore and Rovath Sandeep Singh, by Springer. Integrated Low Fidelity Model for Fuel Air Explosion 2013, a restricted report from ACRHEM to HEMRL DRDO, Pune, submitted to co-authored with Professor Arun Agarwal, Professor Rajiv Wankar, Dr. Aparna, Srimati Vijay Lakshmi, etc. Dr. Rao contributed enormously in the project of national interest. Few to mention here are mathematical model-based control system for swing-out operation for the liquid nitrogen feeding boom for rocket launching pad in Sriharikota. Another one, design of optimal driving profile generation for diesel locomotives for Indian Railways. Another one, mathematical modeling for 6 degree of motion platform for building driver training simulator. Another one is mathematical modeling fuel air explosion system for Defense Research Development Organization. Another Optimal design configuration methodologies for aerospace applications with the IIT Bombay for DRDL. Another one, modeling and simulation of scene of offense crime numbers 42 and 43 into 2015 for the special investigation team. Another, real-time data study and analysis Medha Servo Drivers Private Limited 2017 to 18. And another one, adding intelligence to second generation ATGM Gen Technologies Private Limited in 2018 to 2019. This is a brief profile of Raghavendra Rao Garu. Now we are very fortunate to have with us now Raghavendra Rao Garu. Thank you, sir, for as and when I requested you, okay, to deliver a talk to our participants, you accepted. I really thank you. Now you can continue your session, sir.
Thank you very much. Good evening.
Good evening, sir.
I am switching off video. Are you able to see my screen?
Yes, sir. Yes,
my
sir.
screen is visible?
Yes, sir.
Yes, sir.
Yes, sir. Okay.
Yes, sir.
Thank
Yes,
you.
sir.
Thank you. Okay, I am approached you to give a talk with the inputs of the brochure. So then I felt, let me think of giving something of the related with the image processing. So the title turned out to be the statistics for statistical methods for image processing. This is a broad title I felt. Let me see how much I will be in a position to give additional knowledge to you people. I try to start right from the basics and try to explain some of our contributions from our side, with the intention that it may inspire you to take up some project works or maybe some PhD problems. That is the idea in this talk. So as per the organizers, the topics thought are this. So out of these topics, the present topic is likely to cover which are on the red will not be done. So image enhancement, you will find some inputs, segmentation, compression you can find, linear algebra implicitly will be covered, statistical methods for machine learning is going to be there, and machine learning in image processing. So these are the topics of the indicated topics by the organizers. These are the subtopics likely to be covered in this talk. Fine. So let me, this is a signal and image. These are the two things are basically emphasized. I'm focusing more on the image. I avoided now signal totally now. So image is has various perceptions. So if you take the image, mathematicians can view the images in a particular manner. Optic, those who are in optic, and that is the physical sciences, they look at image in a particular way, and the medical domain people will look the image in a particular manner. So there is a different perceptions are there, and because of the various reasons, the image representation and other things can lead to different formats. So one can look at all these things in a different angles. So what we need to look when you say image, the formats, what are the various ways of representing, that is movements, a graphical representation, entropy, and run length encoding. There are various other things, and the image is specially viewed as a spatial data. That is the beauty, whereas the signal is viewed as a temporal data. So basic difference between the signal and image is image is a spatial and signal is a temporal. So there are various methods are there because of the spatial thing. So there is one of the beautiful technique which is developed by the geophysics people, geology people, which is called as a DAYS, design and analysis of computer experiments. And this is one of the things which is likely to be more useful. And definitely, as you people are from ECE, you know the quantization is very important, and analog to digital converters. So how to make analog to digital and other. I'll try to see whether I can through a small, a different view, A to D converter by using some of the machine learning things, which is a went into one of the MTech projects of our student. So there are various applications are possible, and those applications has categorized into the representation, enhancement, compression, and edge detection, segmentation, and especially content-based image retrieval, content-free image retrieval, OCR, document analysis, medical image analysis. These are all the various applications. Now, other more promising is video analytics. So video analytics is one of the prime or hot area today, and which involves a computer vision. So these two things I have not listed here because when you go to the video and computer vision, I need to bring time also into the picture. So today I'm avoiding the time factor into the whole talk. So I just last 2 days I'm working and I just jotted down some of the points as agenda, and the talk is roughly for 2 hours. I hope I will be able to touch upon these things. I'm not going to the depth, but I will try to touch upon to inspire you to take these things forward. So this agenda is like this, and some of the slides presentations are not mine. I have borrowed from the web. If you people feel that it is known to you, I can skip and I can spend more time on the conceptual thoughts which I am looking at those. So this is it. So image formation fundamentals. Please, any one of you can give me the feedback whether this need to be covered or not, because I don't know what are the things done up to now. So image format, this is from the net I have picked up. So this information is needed for the purpose of answering various questions which are very challenging today. This image is viewed as a two-dimensional spatial. That is, you have a rectangle. A rectangle is a base, and each and every point in the rectangle is getting represented by certain vector. So that way it is a spatial data. So if it is represented by only one numerical value instead of a vector, if it is represented by scalar, then it looks like a matrix. And this is referred as a gray image. Suppose if it is these values instead of these numerical values spread over some A to B, if it is taking only two values A and B, then it is called as a binary. It is represented by 0 and 1. Further, instead of A and B arbitrarily, you can have A as 0 and B as 1. So that is binary image. Okay. So when you come to the color image and other things, each point, each spatial information will be represented as a vector. That vector is called as a RGB. Then we call that as a color image. And in general, color image is given by RGB. Please, is this level information is needed, or can I skip these things? Please, one of you, please tell me.
Please continue, sir.
Yeah, fine. Thank you. So when you look at the some object, how we are able to see what is happening, that requires a certain physical sciences. So that comes, there is a light source falling on the object, and that is getting reflected and our eye is catching. So this structural and interactions are very important for understanding what is getting captured in the image form. So this helps a lot for the purpose of resolving some of the issues, like if there is an accident and we wanted to there is two cars has a collision in one junction. So who is wrong? What type of things happened? So for understanding these things, we need to have a lot of inputs. So this type of knowledge, though it is now we are speaking about the light, there are several other things that is called as a optical ray. Some sort of these things we can use, and we can analyze those things and get a reasonable answer, and we can attach probabilities for the possible events among the listed possibilities. So depending on the physics and other things, how the image is getting formed and how the image is represented by numbers, and those things are coming, there is a transformation. That is, all these things are analog things are getting into this. So there are some normalization is taking place. So what is getting stored is some sort of normalized, or some transformations are taking place, amalgamations are taking place. Then when you come to the digitized representation, these continuous values are getting into discrete representation, that is countable set representation. So that is there we are coming to A to D converters. So these are all fundamental physics that you have. So depending on the size of the image on the screen, on this we are going to speak about the height of the object, width of the object, and this. So these are the things which are coming into the picture now for the purpose of video analytics, and who is abstracting whom. So that is so there are serious research problems are there, which is called which are named as inpainting. So you need to remove the thing which is in front of the other thing, which is abstracting the view of what is behind it. So this is Google Eye came up and they gave a tool to remove all the bars which are coming in the way of looking at the lion which is in the cave, which is in a zoo. You see the bars and other things will be abstracting. Na? So to remove those things, there are some. So which is front, which is closure, which is back, which is front. The depth analysis, all those things can be done. With but those so the depth can be further enhanced. Analysis estimates of those things can be enhanced by using today's latest sensors. But we can also
Raghavendra sir, can you
Sir,
please
we are not able to hear you.
Raghavendra sir, can you please unmute your mic, please? Yes, sir. Now it's
okay.
Okay, sir. Carry on, sir. Thank you.
Okay. So there are various sources of light can give the various kinds of images, and that has its own impact. That is X-rays, infrared rays, ultrasonic, and this, especially the infrared rays or night vision. These things are there. It is stuck. Okay. So there are various thing. Now today we are having various kinds of radars, and those things are giving us to analyze the depth, orientation, many things. So by using these things, today we are coming up as smart city monitoring systems. Okay. So you have, I'll come to that point once again. So there is a, depending on the available memory, we we wanted to represent by 0 to 255, or you wanted to represent by only 32 values or 16 values. So you can see the definition of the image will be changing, and the memory requirements, resource requirements are going to be different for the different way kinds of digitization. Okay, and the beauty of the human brain is it works non-linearly. The thought process is non-linear, and processing is non-linear, and many things are non-linear, but our tools are, our inventions, our uh, uh, tool development things are influenced by the linear. So that's the reason we are not in a position to match a lot of things. So but because of the power of the brain, we can think of having various kinds of manipulations such that the representation can give, brain can read in between and can understand, even though if it is not much. See, for instance, if you take 8 factor, that means 8 by 8 matrix, you take from that one a cell value only we are using. So if you use that, the image will look like the fourth one in this. So there will be staircase effect, and distortion will be there. For the computer, it is difficult, but human being can understand this. So the efforts are taking place to restore the image. So that's the reason when I am using the bandwidth, when I am sending this image, I may send it with a very poor quality of representation. That means memory saving, but the image enhancement techniques are other end will give me back as if it is sent with a high quality. So these are all there. So there are different formats are available: GIF, PNG. I am not going to the details of this, what type of thing. So each is having its own mathematical model behind it. So certain things will be using the fast Fourier transformations, certain things will be using the wavelets, certain things will be, so there are various transformations are taking place on the image, which is leading to this. I am going to speak some other formats which we proposed. Okay, this is the one. Now, what are the different stages and other things, and associated I think here we will find the satellite imaging and all these things. Okay, so now we have a X-ray. This is not much. It may not be having much clarity. So by using some of the image enhancement techniques, you can get this, and you may be able to locate the hairline fracture of the bone. That is a possibility, or a lung infection. You can be. So that is a printed circuit board enhancement. A satellite image or a aerial image can be improved to know the ground. So this way there is a lot of opportunities there now. Though things are very bad, I hope you people heard Nokia phone. The beauty of the Nokia phone first stage itself is that when you take the photograph, they used to take 4-5, one click used to be 4 to 5 snaps. It was taking the 4 to 5 snaps, and initially they started best snap was saved in your phone. Later they used the 4 for constructing the other one, which is much better than what is the best of the 4. So that way they, they have brought up they've used image enhancing tools for the giving. So how these things are going to be, what mathematics, what statistics is required is my focus will be that. So there are various and because of the computer graphics and other things, and we can also create a lot of animation, and we can have a lot of artistic, and you can create a pictures by adding persons, adding objects, and many things are possible today because there is a lot of editing and enhancing possibility processes are there. And when you take the medical domain, so they basically the edges, that region of interest, how to get the region of interest. This is in the medical domain. And when you take the other one is Google part, the objects recognition in a scene. So you wanted to say whether the cake is there or not in the scene, whether there is a candle or not, whether there is some other object, whether so-and-so person is there or not. So all these things can be understood, analyzed today, and you can label the objects in the scene, and hence you can give a title to the scene. So there is a possibility of doing all these things because of edge and region detection methods. Okay, so there is a way of understanding the earth and many other things, and especially water and manufacturing. There, in fact, there was we visited one company in near Pattancheru area. They were using this image processing things for bottle quality. So whether the bottle has any puncture or not. So those things were analyzed by using image processing techniques. The shape and texture, many other things are used in this. So there is a production line can be automated a lot by using these things. So there are many applications are possible, and you can understand in depth, localize, globe, and you can also have a overall understanding. And this is the one which is very interesting, is that if you take a number plate photograph of a moving vehicle, you will not get that number plate information properly. So we can do the processing and we can enhance that, and we can get a more crisp information from the number plate. So these are all enhancing techniques. So similarly, fingerprint analysis, face recognition systems, all these things are possible. And there are various other things. That is, what you look at, this is some sort of bounding rectangles are there. So you wanted to have some sub image you wanted to focus. Especially these bounding rectangles information is more needed today for the purpose of tracking an object in a scene, and it is more required for the sign language. So suppose what is the deaf and dumb fellow is communicating to us. If the video is given to us, we must be in a position to convert that into the text or a speech. That is possible by using this type of techniques. Okay, these are all standard things which are available. Just I am scanning like this. Okay, this is a little bit of now today these techniques are in use for the smart cities. So whether how far the smart cities come up in a structural point of view, that is the buildings, and what is the whether they are constructing a building as per the approved norms or not. All those things can be studied by using IoT technology, drone technology, and video processing, and comparing with what are the approved and other things. So there is a lot of scope for integrating and developing a complex solutions for the complex systems which are real world problems, which are basically real world problems. So this is one of our contribution which I wanted to share with you. See, this is there you have RGB, and we have different kinds of representations. So there are different modes of representations are there. So there are besides RGB, you can have AB, HS, and CM YK, all these things. So you put all these representations and carry out the principal component analysis and take only three principal components, and we name that as a hybrid color space. We named this as a hybrid color space. Okay, this is work of a PhD work of Goswami. Okay, so if you take this, how I can remove this bar? Is the bar is also visible to you?
No, sir. No, sir.
Okay, okay, fine. If it is not visible to you, fine. So if you take this color image, B is a color image, the associated gray image is this LEB LEB representation format is this, HSV format is this, and C, this is each is a CMYK separately, and then it is our hybrid color space representation is this. So we came up this format for the purpose of understanding the outdoor scenes. Okay, so just that is one. Now representation of an image, I will focus on this. So there is first order representation. Now more on statistics related things. Now first order, second order statistics, and first order and second order mathematical things. SVD, principal component analysis, hue movements is the topic of this present module now. To start with, one need to have idea about the data that you are having, so that you can look at the outliers of the data by using Box-Schweitzer plot. So if you take this data and plot, construct the Box-Schweitzer plot, there's a quantile 1, quantile 2, that is the median, and quantile 3. That is, you have the 25%, 50%, and 75% points are available here. And then there is a formula to construct this line and this line, which are called as the whiskers. And this is a box. And one other line extension, this both sides, and another dotted line extension, this. So if your data observation falls within this, then it is called as a well within the limit. And if it falls into these regions, then it is called as outlier. If it falls into the dotted region, then it is called as extreme value. This is in general, people who are doing image processing, they will not do this, but I advise carry out this also, and not only just image processing, even speech processing or any data analytics. I advise to go carry out this, and which is a part of exploratory data analysis. This gives a lot of information. Suppose if you take in terms of the white noise is something, and what is salt and pepper noise? How the salt and pepper noise is different from white noise? And if you look at the influence of the salt and pepper noise on the object or a data and white noise influence, you look at, there is a difference. So if you take the salt and pepper noise, say that is expected to go into the outliers or extreme things. That will, those things will become odd representators in the neighborhood. Whereas if you go to the Gaussian noise, it will be smoothly gelling with the neighborhoods. So it will be vague. Whether it is a still really an outlier or not, it becomes a vague. So this Box-Schweitzer plot gives you a feel of this. Say the whole machine learning is suffering big today because we are not looking at the causal. We are blindly going with a model which can explain, but the explainability, that is the reason to build the reasoning, we don't have the much. So that's the reason we are suffering in the machine learning, which is there are some failures in the real world applications because of this problem. So there is a need for building learning and models which are causal. So we need to move towards that. For that purpose, it is required to understand right from the scratch. Okay, and then you have a descriptive descriptors. There are several descriptors are there. Well, those things are first order, which is the central tendencies are the first order, and the second order are the variance range related things are second order. Higher order will become third moment. Skewness and curtices type of things are the higher order things. Even in the coming to the image, that is generic movements and hue movements are higher order representations of this. So there are the descriptors. Whereas in the mathematical thing, count is a count and sum and average are the first order, and differences and second order differences are higher order things. So yeah, you in image processing we use mathematical also. So I will discuss these things also, demonstrate those things. Now, if I have a statistic data, how we are going to give a statistical representation, how you are summarizing this. So you have some data. For the sake of synthetic data I generated, I have generated 25 observations, and those observations by default there's a normal distribution, and the size of the data is 1/25. That means it is a row matrix. This is the data I given. So once this data is given, I have written a Matlab code because this workshop is in Matlab. I wrote this code, and that returns, this function returns the mean, median, mode, harmonic mean, geometric mean, standard deviation, coefficient of variation, minimum, maximum, range. Okay, so the associated Matlab syntax are here. I have just provided the associated Matlab syntax here. Okay. I have not explored the complete built-in functions. I used simple built-in functions for getting the required answers. Fine. So this is what we have. So once you apply on the previous data, this data, you are getting this. So this is the description about the. So if you take the data analytics, the first stage of the data analytics is a descriptive statistics. So this is falls into the descriptive statistics, and the histogram, box fixed plot, QQ plots, all these things are all stem and leaf plot. Varieties of these plots are also falls into the descriptive statistics. Fine. So this is the first part of the data analytics. So you can, once you have received an image, you can do these things. And so if when you come to the image is not a one-dimensional array. It is not a row or it is not a column. So this will become it is a matrix. We understood image is represented by spatially by rows and columns. So it is a matrix. So how we are going to understand about this? How we are building the descriptors for the image. So this is the analogy of that. So you have a 4/8 image, and that will be converted as a row. Once you convert it as a row, by using the earlier formula, you can get the mean mode. So this becomes a description of the matrix, data of the matrix. Okay, that means we are ignoring the row and the column ID, and we are taking that as one observation, and that we are getting this. Right? And associated things. So how? But this is not the intention of representation. So we need. So what we are going to do? We are going to define further. We are taking a template window. We are taking a window of size 5. And by using this window of size 5, we are planning to represent the window by description. By using descriptors, we wanted to represent the window. So that led to adding W minus 1/2. That is 2. Adding 2 rows above, 2 rows below, 2 rows left, 2 columns left, 2 columns right. By appending this, you will be getting a new matrix. So the middle portion is intact of the matrix what we have. So this is called as a appended matrix, appended data. Now you take a window of 5 by 5. So this is what we have. So you take a window of 5 by 5. You compute the descriptors of this by taking the converting this as a row. Okay, converting this as a row, compute the descriptors of this. So that descriptor is attached to the middle point of this window. So at this point here, so that point refers to this. So the mean, it is the mean. So mean of this window is this. So mean of this window is this. So by each and every cell, that means you started with this matrix. For each and every cell in this matrix, you have corresponding descriptor. Okay, you have a corresponding descriptor. So this is a mean. So mean will give a matrix, a median will give a matrix, and standard deviation will give a matrix. Coefficient of variation gives a matrix. Mode will give a matrix. Harmonic mean will give a matrix, and geometric mean will give a matrix. Minimum gives a matrix. So this range. So all these things are referred by the domain experts of image processing or this called as a filters. So you can have various filters. So this is called as a mean filter. Median filter is this, and the earlier one is the mean filter. So these two are popular, and one can construct the customized filters in this. I think that today you have possibility of constructing this type of filters in Python also. So this, look at, if you critically look at these things, you will get a lot of things. There are certain flaws also there. So when you are computing the harmonic mean, what will be 1 by 0? So there is an output, but the output is, we must be careful. So what it is, what this package, what these computations do going on inside is they are making certain conditions. So if it is 0, here they are ignoring things. So that's the reason it is. What we mean by a log 0. So wherever some problems are there, mathematically the problems are there, those are all addressed by the developers of that package and this. So if you are using Python, we must be very careful, especially on this, because there are few errors were there earlier. Some of the things are rectified today. Okay, this is what you have is this. I have a Matlab code and other things. I am not going into the Matlab code demonstration because of this time problem. When you go to the image, I have taken the Lena. So you take the gray image is this gray. I am converting into the gray, and the descriptors of the gray is this. That is the size is 400 by 400, and we are converting into the ray vector, and then you are computing this. So the Lena grayscale description is this. So I can convert the whole image into one description data. So you see the space required for this is very less compared to the space required for the image. It can be viewed as a compression, but is it possible to get back this? Is a question mark. I cannot guarantee that I will get back the things. So it is a lossy. It is definitely it is a lossy. What extent the lossy? Those things we need to see depending on the inversion, what type of inversion I can do. The histogram of this, and there is one thing is a history is there, and IM history is there in Matlab. IM history gives this type of thing, that is image histogram, and it does even for color, and it is, there is a difference between the histogram of the data and IM hist. And box plot of the data, then QQ plot of this is this. Okay, then I told you that we can compute the movements, higher order movements. So this is you have the sum, mean, variance, third order movement, fourth order movement, skewness, kurtosis. So we can have these measures also, which are a higher order measures also there. So by taking this data, these descriptors along with this thing, it becomes a feature vector for me in the machine learning in future. So if you take the W, the average is something minimum, okay, minimum minimum filter, median filter, and mode filter, mean filter, all these things. So you from one image you can construct many images. Now I am explaining you the mathematical higher order thing. So these are the I skip some of the things now. So there are two filters are more popular. One is order 3 and the other 5. And how we are going to construct the how people constructed and how we can do generic manner. So take a 3 by 3 third order orthogonal polynomials. These are the orthogonal arrays given by the Fisher. So you have 1, 1, 1 is a aggregator, and there's a -1, 0, 1 is a contrast, and 1, -2, 1 is a contrast of contrast. So this refers to the second order. So the first order contrast is this, second order is and 0 order contrast. So you have this. Now you can define a canonical product of one vector with other. So you take the 1, 1, 1 and canonical product of this 1, 1, 1. So that will be nothing but the transpose of this, and it leads to 1, 1, 1, 1, 1. So this becomes a mean filter. If you divide by 9, then it is a mean filter. So if you apply this, you are going to get mean filter. And if you take 1, 1, 1, 1 and 1, -2, 1, and if you apply this, you will be getting this. So what type of this? Along the x direction, it is equivalent to second derivative. It is equivalent to second derivative. So it is one type of filter which speaks about, which is useful for the purpose of edge detection. So if in general, that is I have a 3 by 3 matrix, that 3 vectors, 3 into 3, there are 9 possible operators I can have. So this is the average, that is the median filter, and these things are contrasting filters. And among these, this is a well-known filter. This is another well-known filter. This is a well-known filter. This is well-known filter. This is, and these things are not in the literature. We have not seen these things are used in the literature for the purpose of, or somebody have not given the names for these filters. So there is a scope for doing constructing various kinds of filters. In fact, I did a Matlab program to demonstrate you why only this orthogonal polynomials. You can construct another orthogonal polynomial set for which will do a lot of work, give away some variant of this, obeying all these properties. So once you have orthogonal polynomials, you can apply this sliding window protocol, and you can generate images with these orthogonal polynomials, and you have new images. Those images will help you to understand the details hidden in the image. So you can read a lot about the image by applying this. So whereas it gives a mean, and with this gives a contrast, so it gives you one sort of edge, and this is a second order edge. That means whereas this is a slope and this speaks about the curvature, you can get something about the curvature side. So, and this is Sobel. You say this is a Sobel filter. Look, that like this you have, and if you take 5 by 5, you will be having 25 filters. 25 filters. Fine. So that means whatever I demonstrated about the statistical representation, descriptive way of rotating an image can be done by using mathematical, which are by using these filters. So let me now come to the representation by using SVD and PCA. So SVD in MATLAB, if you give SVD of X, it returns the three matrices USV. USV will be equivalent to gives the X back. X is equal to U into S into V transpose. So now I can write S U into S to the power of half as one matrix, S to the power of half into V transpose as another matrix. So I have two matrices decomposed. X is decomposed into two matrices. And this is called as this in general referred as a semantic representation. And I hope some of you who are doing research in the latest areas, that is a topic modeling. So one of the fundamental technique used in the topic modeling is this. So they use this if you have n objects with a feature space. So the n objects representation is, this is called as a semantic representation of the objects. And whereas this is called as a feature semantic space of the feature. So if you take these are the people, and the above one is different kinds of movies, that is family type, the comedy, horror, some sort of these things are there. So if you take the score matrix of the different people with the different things, that can be decomposed in, and this gives a semantic representation of object people towards the watching a movie, and the semantic representation of the directors and producers. This becomes a this information is used for the purpose of directors and producers for the semantic representation of features. That is what type of horror, how horror movies need to be looked, how the comedy movies need to be looked, that information is coming. So that is the beauty of this SVD decomposition. Okay, I'll come back to the bottom graphs a little bit later. And now when you take the PCA takes the same X and they compute the variance covariance matrix, and the variance covariance matrix will be decomposed like a SVD, which is called as a spectral decomposition. And this, so there is a Matlab command PCAX is there that gives you coefficient, scores, and latent. This will be, so the X is nothing but scores into coefficient transpose. It is something like X is equal to use SV transpose. Here it is. So you can now if you have a X is a matrix and S will be the matrix, is a rectangle matrix which will be containing only diagonal elements, in general non-negative, and whereas this is a n by n matrix, diagonal matrix, and this is. So these are all the principles. The diagonal elements will indicate the representability. So the cumulative first S1, S2, so on Sk, and here lambda 1, lambda 2, lambda k, and take the cumulative sum and the percentage over the total is that this curve is this. So this RGB, R and G and RGB. So three things of the. So you take the representability. These things are RGB separately. These are the things here. So here similarly for RGB for the Lena, you take this. Now it is very interesting thing to observe. Can you contrast these two pictures? Anyone can tell me what is the difference between these two pictures? Okay, fine. So now you look at it started with a steep slope, but it has become, the slope has become very less, fallen down. A drastic change is there in this. So it has become a marginal increment. The gain is marginal. Initially it is high, but afterwards is marginal is high. So to get some sort of 90%, I need to have 250 components. Whereas the PCA, you say it sustained its steepness. It sustained steepness, and for getting the 90%, I have somewhere around 30. 30 components are enough for this. So this indicates a lot of information, and principal component analysis will give a better compression compared to SVD in Lena case. I'm not generalizing at present. Sorry. I don't want to make generalizations. If I wanted to make a generalization, I need to prove a theorem. So what theorem I need to prove? The number of components required for principal component representation is significantly smaller than components required in semantic representation by using SVD. This theorem need to be proved. Is a challenging problem for the mathematicians. Clear? So this will tell that. So at least for Lena, I recommend I go for principal component representation. So I can get better compression compared to SVD. Okay. So how these pictures will look like? This is a RGB over. So if I take one component, I am going to SVD. This is the representation of one component. You see, slowly image is getting enhanced. So it is a cumulative. It is a cumulative. Are you getting? So by taking 44, I am getting 66% definition. Definition of the Lena image, 66% is covered by 44 components. It's gently increasing. Okay. I'm doing a bit fast because 400 images will be there. After some time, you are not, once it is 92, say 170, it is 92. Our eye is not able to distinguish much. You can see there is a scope for doing small research here. I'm not explaining that part now. It will be nice if you see the Matlab execution, but it will take a lot of time. That's the reason I have prepared. So for 400, you see there is no difference. So now the problem also is that what is the distance between two images? So you need to come up with a metric, your own required customized metrics for computer saying something is better, it is better than that. So for establishing these things, you need to have that. Okay. Now you look at the PCA, the figures of PCA. So R, G, B together. So now you see one component, it is more or less same as like SVD. Two components is more or less 3, slightly better. See, 10th component is giving me somewhat picture about what is the real picture. You see, by 25th, I am able to get more or less as good as the original. Fine. So you can see there is a definition. It is highly 92% is covered in 44. So that is the advantage of the thing. I am not going to the further in this. Fine. Any questions at this point? Invariant movements. So X is a random variable, univariate, real random variable. We can define the mu, and Raw movement is defined as x to the power of r into fx dx over the range support, and central movements are defined x minus mean to the power of r fx dx. So these are the central movement. Now when you have a two-dimensional thing, it is defined as x to the power of r into y to the power of y to the power of s, f of xy. There is a f of xy is a bivariate random probability density function. This and central moments are defined like this. So you will be having two suffixes in the two-dimensional case and one suffix for this. Now you see that if you now we need to convert this definition to the image. When you take the image by the definition or by the representation or convention, we are always representing from 0 to 255 in the grayscale, and the vectors are 0, 0 vector to 0 0 0 to 255 255. So taking this way, so f of xy, the value is not adding up, though it is positive, the area under this function is not equal to 1. So that is the difference we have. So we need to convert, we need to engineer it such a way that we will be in a position to get back to the definition of the moments which we have in the random variable. So we define MRS, a simply integration in the case of analog images. In the case of digital images, this is the way we are right. So M00 is a definition, is the in analog, and simply the sum of all the possible values in the grid is this. Now, when you take x to the power of 1 and do that, that is called as a M10, which is mean of x, and M01 is this, which is called as a aggregation with respect to y. Now these things will become mean, respect to means, if you divide, because this is not probability density function. It is not obeying the probability density function. Though it is non-negative, the accumulation is not 1. So to normalize it, this is the way we need to do. So the mean is this, mean of x, mean of y is this. So this is the way we compute. So in general, we have MRS and x bar, y bar. Now we define the central moments. And once you define the central moments in this way, you have this. Now we are defining eta rs as the central moment divided by the normalizing factor for the compensation of the probability with to the power of gamma, where gamma is SR plus S plus 2 by 2. So this is a little mathematics needs for this explaining the derivations and all. Now the real Q moments are defined as, after computing eta 20 plus eta 02 as a xi1, phi1, phi2 is this, phi3. These are all some formulas. I am not going to the derivation of these things. So at present we take these formulas and use. So automatically we can code it and we can get these results. Now when you give it, any doubt? Any doubt?
Continue, sir.
Okay, if you give this input image for that invariant moments, you get these invariant M1, M2, so on. M1 are in. Okay, these are all additional things. Fine. So you for a given image you can have invariant moments, and some additional descriptors are also you can add. So this can become a feature vector. Okay. Now the beauty of the invariant moments is you take a Lena and the corresponding histogram is this, and the corresponding invariant moments are this. M1, M2, so on, M7 are the invariant moments. Now I rotate the Lena 30 degrees, 60 degrees, 90 degrees, 120 degrees, like this. So if you rotate this, for corresponding histograms are this, and corresponding invariant moments are this. You see the beauty. Invariant moments are more or less same. The values are same, but there is a slight difference in the histogram. This difference is because of when you rotate it, there will be zero padding will take place. That's the reason you find a peak at a 0. It is something like a noise. So there will be a impulse. There will be some impulse proportionally depending on the white space created because of the rotation. So this is so you will find at zeros there is a nuisance part of a frequency part which is coming here, and when you rotate it 90 degrees, that is disappeared. And this when you rotate 90 degrees, you will find the original histogram and 90 degrees is same. So if aligns, that is, if there is no white space, zero padding is needed, the histograms will be the same. So these 4 histograms are the same, and whereas where there is a need for zero padding, it will become there will be a high frequency will be there at the zero frequency. So we need to, this type of information can be used. How much rotation we need to do, get it to have a image registration. Say image registration is another issue. So one can look at this histogram. Rotation invariant movements will not be able to capture, whereas histogram is expected to capture something of that. Then these are all the various kinds of representation and various application. Another set of applications you have image histogram equalization. Now, if you take x is a random variable and y x and y are 2 random variables with respect to frequency distributions, cumulative frequency distributions f and z, then you can have a uniform distribution derived from this. So u will be uniform distribution by applying the transformation f of x. If you apply this transformation, it is a uniform distribution. If you apply the transformation g of x, g of y, sorry, it should be g of y, then it is also uniform distribution. This should be y, sorry for the typo. And you have, so now you can define this. So uniform distribution, u is a uniform variate. You can define v is equal to a plus b. So it is a uniform distribution between a and b. And defining f inverse x, you will get a b. Fine. So you, and v can be, sorry, u is equal to f of x. There is a small error here. There is a, one can apply a transformation. So x is equal to f inverse u. X is equal to f inverse u. I can get that. And this y is equal to f inverse u. And once I have a uniform distribution here, this, so I can get one uniform distribution to non-uniform distribution to uniform distribution to. So that you can see in that. If I have a data which is having a uniform histogram as this, by applying the transformation, I can get the uniform data, uniform distribution. So the cumulative probability distribution of the x is like this, and when you take the uniform distribution, it will be like this. Now, by taking the uniform distribution by forward transformation, I can get this. So if I start with an arbitrary distribution, I can reach a goal distribution. I can reach a goal distribution by via histogram, via uniform distribution. So from x, I can go to a uniform distribution. From uniform distribution, I can reach to the target distribution. This is very much useful in control systems. My input is follows one distribution. My output need to be follow one distribution, and this is via. So the composition of these 2 operators is my characteristic curve. That gives me a very good control system for, and it will become a part of the calibration. So from here, from here to here, I can come to this by via this, and this input is calibrated to give this output. Now, if you take this Lena grayscale, the histogram is this by histogram equalization. So you see the contrasting thing. So this is the original image. By a histogram equalization, you find a little brightness, and some definition is very clear. Fine. Look at what is happening, how this is useful in various applications. Can this be applied to the beauty parallel? about these things. So now my Lena is having this. We studied this, how to get the histogram equalization. Now my intention is to go from Lena original distribution. From this I wanted to have exponential distribution. I wanted that this original Lena distribution is this. I wanted to have the data should obey exponential distribution. So I am going from here to uniform, and from uniform to exponential distribution I am coming, and you see how it will be. So this is from here, and if I convert that is so is it giving you hint that how I can hide the information? I can hide the information of this by applying some transformations, statistical transformations. There is a lot of scope for visual cryptography. Fine. So histogram equalization, and this is a in olden days, I don't know today whether we have in the TVs the contrast adjustment. So earlier we used to adjust the contrast. This is the contrast adjustment effectively doing. This is what is happening in. So this contrast, what is there in this contrast is ultimately brought to this contrast. The second one, now I am moving to other wrap of representation, which is EM algorithms. This is for the segmentation and compression, analog to digital converter, OCR, topo map. Many things can be done using this now. Expectation maximization is fundamentally for the purpose of understanding the mixed distribution. Let X be a random variable with PDF F, which is nothing but a generalization of a few PDFs. Whereas G1, G2, so on, GK are the probability distributions given, and though the F is a mixture of these things. So where alpha i's are non-negative quantities and add ups to 1. So once I have this Fx is equal to summation alpha I gi x theta I is equal to 1 to k, will become another probability distribution when G's are probability distribution. So both will obey the property. though GIs are a unimodal, this F will violate the unimodal property. If there is a well behavior of the curtices will be there here, and this will be having a highly disordered curtices. So the curtice is the fourth order movement, that is a higher order in representation of the data, will speak about, give a hint about can that be pure or a mixture. So I can use it in my data analytics and data modeling and data science environment. So X is a random variable, it is a mixture, and it's a mixture of YIs, where YI is having this. So this is a, so it is in a way, independent component analysis, which you might have exposed to the speech. When you take the speech and sound signal, you have the source and mixer, so that you can find it out independent components. So YIs are independent components, and X is the mixture of those things. Now, given data set, I don't know why. Given data set, I need to characterize the Y. So that is effectively estimating the parameters alpha i's and theta i's, assuming the probability structure G. If I assume the probability structure G and try to get the feel about this, then get the feel about this mixture nature, then that is called as a mixture model, and that is the activity classified as named as a expectation maximization algorithm, EM algorithm. Okay. So if G further is normal, if it is assumed to be normal, then this is called as a Gaussian mixture. Fine. So it is a simpler Gaussian mixture. Gaussian is well understood. It is relatively simpler, and it behaves elegant way in mathematical point of view, that calculus point of view also. That's the reason Gaussian mixture models are more popular, and even most of the speech analysis is carried out by using Gaussian mixtures. let me go to the one of our study by using this in a OCR. OCR is a true machine learning technique which is developed by us. It is a real machine learning. It is not namesake machine learning. It is a collaborative work. It is one of my MTech student work where these two people are also collaborated at that time. So you take this mixer. We because of OCR we were interested. We looked at the OCR is can be studied by using mixture of two distributions. I'll come back to that a little bit and simplify that. We go on for the Gaussian mixture and the estimation process and other things. I'm just skipping this. Now let me explain the philosophy behind why hyperparameter k is equal to 2. This is one of the important thing in the whole innovation. How human brain is superior compared to many things is that this spark. What type of things need to be embedded in our process of research is very interesting. And that so when we look at it, if you take a whiteboard, you cannot read anything. Can you read anything on the whiteboard? Is it possible to read anything on this corner? Can you read anything on this corner? You will be able to read something on that corner if so what is happened now? There is a background and something is foreground came into the picture that made you to read something. So when you look at the OCR, this is the flash idea occurred to us, and we look, this is a background and foreground. So once this flashed, we started looking at the image analysis. So we took the various characters printouts and we take the character, and because it is a foreground and background is a binary, so the histogram of that is this. Fine. You have this. So zeros are here, ones are here. Fine. Now I think one is a foreground and zeros are the background. Now what? This is a binary image. Binary image is not continuous. So that made us to look what can I look at this as a continuous, more or less continuous. We looked at it. Sorry. We converted this, we saved this binary image as a gray. That means we applied binary to gray conversion. Once we applied a binary to gray, you will have a histogram, total histogram, proper histogram here. That histogram led to the EM algorithm parameters. The mixing alpha 1, alpha 2, mean 1, mean 2, and the variance 1, variance 2. Fine, variances are more or less same, means are different. This is a foreground and the proportions are different. So we have taken why it is R? Because of the foreground. So we look this foreground as a contributing for R, and we call this as a feature set. So you look at dimension direction. If you take R by using blind mathematics, I have a 6 features. We slash it to 50% by using the common sense. What is that common sense? Why R is because of the foreground. So the foreground parameters are enough. So we have taken as a feature set as this. T is the foreground information is this. So like this we have taken and we have developed the full OCR in this way. Okay. Now when you take this, we found the problem. When you're scanning, we found the problem. Any scanned image is in a grayscale. There is a lot of other noise is there. We thought of getting rid of this in a one go. So that requires binarization. So we look at it. Binarization is an interesting thing. I'll come to that. So if these are these two by using word source and this, and we have proposed a binarization method. The bottom one is our binarization method. You take an image, this image, color image, gray image, and other things, and this. So you look at our binarization has turned out to be much better in this. So we looked at it. Now, once again, what is meant by binarization? You have a analog value. Analog value, there is a need for cut, which says this is this above and below. So that requires, that means it is a image. A image is a mixture of two distributions. So this is one mixture and this is another mixture. So a point belongs to this mixture is 0 and a point belongs to this is 1. We looked that A to D converter as a mixture of two populations. With that we did, and we got binarization method, and that is the one which we call as our proposed binarization method. That led better results. So then we have the problem of extracting the lines. We have the problem of extracting the words and then characters. So we looked at everything by using descriptive statistics. We took horizontal. After binarization, you have ones. You take how many ones are there in this row, how many rays are there in this. So we have plotted the number of rows, number of ones. That turned out to be one histogram. So there are valleys in the histogram. Valleys of the histogram are the line separators. Now, after that, we need a word separation. Now you have a valleys. If you take projections in this side, then you have histogram. From this, you have valleys. By using the valleys, we are able to get word segmentation. And afterwards, character segmentation. Here you have the problem. So once again, we applied a little bit of EM algorithm to avoid, to understand the vagueness in between. So there is a vagueness. So by using some sort of EM algorithm, once again, we had a cut and we are able to get this. Still, there is a problem. Some of the things are not isolated. You can see that this type of things have turned out to be together. So we ultimately got something. So characters came, and now we need to recognize. So we have taken some character set, and initially now real machine learning is coming. I don't have anything to recognize. My comparator for template, my template set is 0. I don't have any template. I don't have R, E, something like that is not there. So we have empty set. We started, and whatever the characters that we got, we computed the distance between the two feature vectors, the two character feature vectors. By what are the feature vectors? Mixing, mean, standard deviation. By using that, we got distances. Nothing is recognized. Nothing is closer to what. So we have, once again, we applied EM algorithm and found that there are outliers. So these outliers which are going away in the distance distribution, this is once again mixture, which are away and which are closer. The away are the template characters, that is a comparable characters as used as a standard, and we kept these outliers, this other set, as in the basket, and those things are becoming the reference characters. So we kept this into the reference characters. Automatically those reference characters will be recognized because the distance from the basket, the characters which are in the basket, for that character will be 0, is it not? So that is recognized. You can see there will be ones. So initially some characters are not recognized because this character is in the basket. The distance to one of the character in the basket is 0 now. So that's the reason it is recognized, and we have it. So now you once again histogram, if you take, naturally the zeros peak will increase. In the process, the whole distribution histogram move towards 0. So it slides this 0. Once it slides to 0, you land totally. So what is happening in this same is this. So in this manner, we have found something new, and these are added into the thing. So we got the final template, and this becomes a point distribution. Once you have learned about the character, what is that character? I don't know, but I know now. I collected some characters in the basket, and these characters are the templates for recognizing the characters of that text which I am studying. So from the population, I have a representative pages. From the pages, I have decomposed and this. So this is the way we could and we could get this. So there is a lot of byproducts are there in this. So the EM algorithm, image representation by using EM algorithm has a wide applications of this nature. Then I am skipping the all other advantages as a OCR point of view. These are there. I am not going to this. Another application, which is PhD part of the PhD work of Professor Raju Vankar and Professor Agrawal, where it is you look at is the topo map. This need to be digitized. Now digitization was the thing. So if you digitize, there are some names. So suppose it is a 4,000 altitude, and there may be some lake, some name. So when you remove this, there will be gaps in the topo map, contours. So the gaps will generate. So how to fill the gaps? So you take a small window and if this, so how to fill? So whether this is connected to this or whether it is connected to this, which one is connected to? So you look at it, is it connected to this or is it connected to this? It may be connected like this. So we need to know which is connected to what. So this pairing the endpoints. Pairing the endpoints is one of the thing, and it is a complex problem. So here we applied once again EM algorithm. We got beautiful results and exponential saving of time in this solving this problem. It is a 0-1 binary thing, and once again we saved as a grayscale. That is a thing, and then we applied the EM algorithm. You look at these edges are there. The edges need to, so you will be finding. So when in few iterations, you can see that these edges will have some probabilities. That is, it is initially the 0 probability, but it belongs to this with some probability now. So in iterations, over iterations, there will be a posterior probability competition. Here, not directly EM, a one intermediate step of EM is used. The posterior probabilities are used here, and that so by using this posterior probabilities, you will get a cloud of this nature. So that means these are the segments which are, so the whole problem, that is point, there are n edges are there which need to be weaved NC2, the complexity is NC2, that turn out to be this sub collection. Only K edges are there and the KC2 complexity. It is drastic fall in this. And whereas some of the things are isolated and there is no complexity in that. So the problem is decomposed into smaller problems and it is possible to, so this has become a beautiful contribution in high performance computing. We could do the weaving very well. There is weaving algorithm is also developed for this purpose. So we could generate the topo map, which supposed to be like with all those, which is not having all those obstructions of the or unwanted things. Fine. So next we have another contribution we had is a coefficient of variation for the image representation. You take the image, you take a image, the color image histogram of the RGB, and you can compute the mean, standard deviation, coefficient of variation. And this coefficient of variation, if it is more than 33%, it is 1, otherwise 0. So I can write a vector, a three-dimensional vector, binary vector, which is having this. So for this picture, 1, 1, 1. That means the coefficient of variation is greater than 33%. Why 33% is the question. At present, there is a consistency criteria is 33%. But if you go the book which we have written, you will get more and more insight about this. So we have taken just for the sake, we have a few images around this is what is it? 4, 5, 20 images are taken here. And for these 20 images, the mean, standard deviation, coefficient of variation flag, this for the RGB. So afterwards we have computed the three ones now, that decimal representation from the binary vector we have converted into a decimal number. So 0 to 7. So each image will be getting a flag of number of 0 or 1, 0 to 7. So now the image receiving 0 or 1 or 2 or 7, which is helpful for us for doing the hashing. So I can hash this image. For instance, the first image I can hash to the bin 1. I can hash the third image to bin 5. Look at if these numbers are meaningful semantically, the images collected to that bin are going to be some sort of homogeneous. So this simplifies a lot of our pattern recognition problems, face detection problems, many problems associated with these things. So this is one advantage of the coefficient of variation, and we gave this is one application, machine learning application, and then we have developed the coefficient of variation decision tree also, and that has given a few results, and in fact one PhD was produced in that. This is our book. And you can see. So now these 20 images will be classified into this following distribution. There is a 0, only one hash function, hash value as 1 as 5, hash value is 2 is none, like this. So if you look at it, it is very interesting. We have taken some standard databases, and for one database we got a hash value as only 7. All the images of that database has received only one value. Another database received only 3. That means that they were working with one type of benchmark data images. So whether how to give a how to say that my method, my proposed method is capable, is robust, all these things, we need to look into this index, that hash value, and say this works for this hash value, this will inferior for this hash value. All these things are possible. So that way we felt it is one of the contribution for the groundwork for the purpose for the researchers in image processing. Okay. Now let us come to the another one, which is a spatial statistics. So there was a question came to posed to us. You see, some people will take the photograph of some people, and they remove the face of the person in the photograph, and they embed other person's face. So this is a tampering. So there was a question whether is it possible to identify the tamper, whether the document is tampered or not? Is it possible to identify the tampered region? This is the one which is and ultimately the documents are prepared now. So the question comes here, this new image which is produced, they have to take the printout. So who produced, or from where this printout was generated is become a. So the question came to us as the which printer was used for printing this document. So that question came to us, and we looked at it, and then that turned out to be the analysis of turned out to be one PhD work, and that being it is a spatial information, we used the spatial statistics. This so spatial statistics. This is from the web. I don't know whether if I go there. Let me see how fast I can go. Okay, so you have these regions, and ZI in ith location. ZI is the information which is a random variable. Being it is the index is a location, It is a stochastic process. See, whenever a random variable tagged with a parameter, then it is a stochastic process. If it is a time, it is a time variant. It is a spatial variant, spatial. So it is there is a nomenclature difference is there. Time dependent or generally called as a stochastic processes, whereas this type of things called as a random fields. We call this as a random fields. But basically, the random variable over the parameter. Fine. We wish to understand what is happening, how COVID was spreading, how COVID is under control, how the business is getting impacted because of the policy. All these things we need to understand. So for that purpose, we need to go for the spatial statistics. So when you have this data, we can have the surface, we can build the surfaces, and your reference points are this. From the grid, we make a grid, and the reference points are this, and you are getting based on the value you are making into the regions. So these are the regions of one kind. So the regions we depict by using different visualization techniques, the colors, shades, textures, many other things we use, and by that way we distinguish one region from other, and it will be informative for us. Okay, by taking for understanding this, definitely sampling is very important. So you have this, you sample at some points. Now what you may be sample in a spatial, you take some samples at point. So there are various sampling methods are there: systematic sampling, random sampling. So these things are extended once again to the spatial also. So you take some points, and at those points you take the data. By using this data, you try to build a model. Now the way we have done statistical distributions, fitting and interpolation, extrapolation, all sorts of things, once again it's applied and you will be getting represent. So this is visualization of this based on this sample. You can do a lot of things when the I'm just skipping. So you have a point Z1 at a particular location and another point Z2 at another location. That means these are the readings of this, and these two we have, and then we are computing, we are representing by normal distribution. This is a normal distribution with mean and variance. This the standard deviation is this. Now these 2 points will be having correlation. The correlation is a function of this direction and the distance. So the h is the parameter. H is the parameter which is indicating the characteristics of the distance and orientation of these 2 points. So that is called as a correlation. That correlation we take, and this is called as a spatial correlation. Now this spatial correlation, whereas if you take the time series, the value at this point and value at this time point, and you correlate this, and we call as a correlation with a lag h, and the representation of the correlation over the lag h is called as a choreogram, I think. Okay, you have correlation, that is a variogram, not variogram, that is a choreogram. Okay, so now we have the h, and taking this fixed h, that means these 2 may be having the same h, these 2 may be having the same h, these 2 may be having the same h in the same direction. So taking all those points, you can compute the empirical correlation, and that empirical correlation over the x-axis as h will give you the variogram. That is called as empirical variogram. Okay, this is the one. So you take that lag, spatial lag in a particular direction, and that is expected to be like this. That is when it is a farther distance, it becomes a 0. So it is a complement one. That's the reason it goes like this. So it is initially there will be something, even if it is 0, there may be some variation will be there. So this is called the negate, and gradually it is going. Afterwards, it becomes a saturation, that is called as a ceiling, and this disappears. This once it becomes a stationary, there is no spatial correlation. Additional, there is no spatial effect. So this is becoming some sort of a independent of the space. So if this point, where if you have a one point in a particular in your locality, there is a COVID case, and whether that influences in my locality or not, it depends on the model of this. So if the my location is far away from the location of where the COVID is observed, then it is false in this. The correlation is nothing. It will not have a effect on this. So this is a this called as a variogram, and based on the data, if you do, there is a called as a empirical variogram. Once you have empirical variogram, you can compute these three quantities. That is, this is range and the seal. These things can be computed. These are the first three parameters, and one can model this curve. One can model this curve. That is called as a variogram modeling. Okay, variogram modeling. So this is a the empirical, and this is a theoretical curve. This is called as empirical variogram modeling. So now this is the base for us to work on that problem. I just skipped the other details here. So if it is a Gaussian distribution, that is each is a Gaussian, the variogram, the correlation is a Gaussian model. The variogram will look like this. If some other, it will be something. Okay. By looking at the variogram pattern structure, we can say that. So the estimation process and all these things are explained here. I am skipping that. Okay. So we have that. Okay. Now I am explaining how we have done the printer things here. This is one of the PhD students' work. We have taken the printout, and we have taken homogeneous time color region, because a variation in the spatial variation is impacted by the other artifacts. So that's the reason we have picked up a homogeneous patch. We are interested to extract the information about the printer. So it should not be confounded with other characteristics. So to avoid the problem of nuisance characteristics which are coming from the imaging, so the sampling has to be careful. One must be do a sampling properly such that it will. So we have picked up the homogeneous patch. Homogeneous patch. So this patch we have taken, and this patch has taken from printout of various printers. So we have taken printers, various printers. We have taken the patch of various printers, and we have done the empirical variogram plot. Look at the empirical variogram varies from one printer to other printer when direction is 0. This is the direction is 0. When the direction is something, I am not able to see. Here it is maybe 30 or 45 or 15. So that is it's a 15 direction, angle is 15. This is the one. Angle 45. You can see that the empirical variogram varies, depends on these things, and varies from one printer to other printer. That this gave us, this observation gave us a hope of identifying the printer used for the producing the document. So what we did is we fitted a his Gaussian variogram model, and we have taken the parameters. we have taken the parameters of the estimates of the parameters. These are the Gaussian variogram we fitted. For this, we have A1, B, C1. All these things have become a feature vectors for the one image which we have taken. So we have various printers. For each printer, we have this. So printer ID has become the label, and these are become the features. So in this manner, we are able to get a data set for submitting to the machine learning in a supervised learning. So we have applied some of the supervised learning techniques of for this, and we were successful in identifying the printer. And we extended this further for the tampering the document. Especially a certificate name is replaced with other name. That tampering we were able to identify. Okay. This is a machine learning algorithm applied is a redact based decision tree. Fine. This is what we have. Another special thing is image representation we got by using spatial thing. It is one of the MTech dissertation thing. So when you have a spatially, and this point we need to estimate. So based on this and relative characteristics of S0 with respect to these things, we'll speak about the value of this. So that is the theme of the spatial interpolation. That is called as a kriging. That is known as a kriging. And once you see, I have used 16 GB RAM, and I have used 32 GB RAM. I have used 128 GB RAM, like this. So I executed a program, these things. Now I am having a point which is 100 GB RAM. Okay. What will be the speed? When I computed this alone, is it possible to say something about it? So something of this type of questions we can answer using. So when I execute the program on this 32 GB RAM, even several times, will there be any change in the measurement of the time? There will not be any change. So the beauty of this type of experiments, computer related experiments, the variance of the data at this location is 0. So when I make a reading, the variance of that reading is 0. And it is different from the regression models. What is the happening in the regression model? If you make readings at the same point, you will get a variation in that. So if you write an examination today, you will get some mark. Tomorrow you write, you will get some mark. Day after tomorrow you write, you will get some other mark. So it will not be the same. So there will be variation in that. It will not be 0. So whereas in the computer experiments, the outcome is always same. So the variance is 0. So that is the beauty. That's the reason the modeling of this type of things called as a DACE, design and analysis of computer experiments. So this has attracted a lot, and a lot of applications were developed, and a lot of research, a lot of tools, a lot of solutions were obtained for complex systems like aerospace problems. So this is the model. I am not going to the details of this model. It is appears to be like a regression model, and ZX is a random component, and these are the parameters. So as usual in the regression model, you have the linear coefficients to be determined, and this here you have this random coefficient. There is a correlation matrix. The correlation matrix will be a spatial characteristics is R, and the variance component is sigma square. So the variance is estimated by these formulas. These things we need not to go into the details at present. The theme is how this is helpful for image. These are some formulas. So we have the trend part, and this is a stochastic part, spatial stochastic part. This. So now we have taken an image, grayscale, and we have sampled. Systematic sampling we have done. Effectively, it is something like a down sampling. We have done that, and we applied the those methods. That is DACE algorithms we have applied, basically kriging, and then we got the parameters. So For applying these parameters, this model, based on this data, interpolating values, we get the predicted image is this. So we are able to produce the image from given image. We are able to produce this. The representation is this, and we named this as a like a JPEG and other things. This is a days image format. So in fact, we call that .days. .jpeg we call .days. If it is a color image, you take the components, sample it, and you can have a sampled color image. This apply the kriging days, and you reproduce, and you will get this. So in this manner, we can produce this, and this is a days representation. So the beauty of this is once you have, this is the representation. Now you wanted to use this image for various things. That is, you wanted to use this as a your in your email or anything. You wanted to use this as a in what is that called? We call in the WhatsApp and other places. So you see some photos now. Again, as the name. So you have that miniature and medium something. So these sizes are very. It is easy to manipulate these sizes, and we can be able to get these things because the whole representation assumes a unit square. This image is treated as a support is treated as a unit square. So when you come to the real coordinates, the unit square can become 5 by 5. It can be 5 by 10 like this. It can be anything, and you can do the interpolation depending on your resolution capacities on it, because it is a function evaluations only. Okay, you have this. So when you take sampling rate 2, 3, 1 out of 2, 1 out of 3, 1 out of 4, 1 out of 5, you look at, you will be having the clarity. So more the sample points, that means 50% it will be better. If it is 20%, it will be impaired. So you will be having this problem. So if you wish, there is a possibility of post processing. There is a possibility of applying the image enhancement techniques here and get more close to this once again. Okay, there is a trend model is there. So you can apply the zero model, constant, polynomial 1, polynomial 2, polynomial. So when you apply with the same sample with a different polynomial orders, you will get certain better accuracy. There is a problem in enhancing these problems. There will be if overkill also. There is a overfitting is also there. One must be careful in this. After some polynomial degree, it may work adversely also. So if you take the polynomial and sampling size, overall contrasting is this. So there is a variation is possible for customizing this days approach. Okay. So this is a compression. It gives you a compression. So there is a good amount of compression is possible. Compression rate is 74%. So if you BMP, this our here is the days if days I don't know whether we are. So days compression, you can have a comparison of these. These are different compression thing representations. So fine. So this is what this and now we have discussed a few of the descriptors, and we have descriptors statistical, mathematical, and spatial is now very invariant movements, coefficient of variation point of view. All these things are there. You can put all those quantities of an image as a feature vector. Once you put as a feature vector, you can carry out the unsupervised learning if you don't have the label, and you can carry out the supervised learning if you have the label. So it will be this way of extracting features is a no doubt it is a old school of thought. Because I am not touching anything about the today's deep learning where you need not to do any feature extraction, but this will give a lot of semantic approach, that is a causal. You can give a causal explanation, you can give explainable machine learning is possible here. So this is I didn't get much time to make a demonstrations of image representation with all these things. So this is a thing I I'll just stop at this point because it is almost 9 now. I ready to give responses, clarify some questions or doubts to my best of my ability. Thank you very much.
Thank you very much, sir.
Yes,
I
sir.
request participants, if you have a query regarding the session, so you can ask the questions here. So now the questionnaire is going on.
Good evening, sir. This is Mohammed Imaduddin. So you spoke about OCR and EM algorithm. I just have I just wanted to clear that. See, when the language is written in Hindi, we do not find space because we always write a horizontal line on the top. So how do we differentiate? How do we differentiate the characters in that case? How do we calculate the distance between two characters in that case?
Okay, that is not a big problem.
And what could be the efficiency of EM algorithm in terms of identifying the characters correctly?
No. For the I please, I made a very clear cut categorical. It identifies tokens. It gathers tokens. It is the job of the human to label the tokens.
Okay.
Okay. So it is all possible distinct tokens are possible to capture by the EM algorithm. Nothing will be left out in this. In fact, we did on most of the languages, including Urdu.
Oh, okay.
Yes.
Okay.
Let me, if I can take a little time, let me take one slide here, open slide, explain your answer question. See, what you are saying, the histogram will turn out to be like this. It is 0. Say when there is a gap, it is your histogram will be like this, is it not? When what you are saying is a horizontal line is there, in the case, it will not touch the 0.
Yeah.
This is enough for me. See, what is my EM algorithm? It divides. If you take these values, it develops a cut. Here it is. Here I am taking this as a cut because my knowledge.
Sir, we are not able to see your screen, sir.
Oh,
I
sorry,
think you're sharing.
Sorry. I am sorry. Extremely sorry. This is the problem with online things. Where is the sharing? You will to see now?
Yeah, yes, sir.
So this is the situation where histogram is touching 0. Frequency is 0. Is it not?
Yeah. Yes, yes, sir.
Whereas if you take a Hindi, there is a zero rekha. When you have a zero rekha, it will not be touching 0.
Yeah.
So the histogram will not touch to 0.
Okay.
Are you getting?
Yes, yes, sir. Yeah.
So the frequency will not touch 0. But what EM does, it divides the frequencies into 2 parts. These are all one side, these are all another side.
Okay.
even our binarization algorithm is of that nature. That is the A to D converter. We are able to achieve much better because of the same principle.
Thank you, sir.
Yeah, fine. Any other?
Thank you. Thank you. Thank you.
Any other question?
Yeah, members, please ask your questions if any.
Good evening, sir. I am Mohammed.
Oh.
Sir, maybe this question is not related to image processing, but I have a small query related to the signal processing only. Suppose,
Fine.
sir, if I am recording on voice and
Okay.
doing the same, can I use the same algorithm in this one?
Oh, okay. Initially I thought of covering speech as the signal as well as image, but I felt later it will be too heavy. You see how much different things I covered in image. By using EM algorithm, we produced the gap rim. When you are speaking, there may be some white space, no?
Yes, sir. Between voiced and unvoiced signal.
Yes, we identified and we removed that, and we could reduce the length of the speech. We could do that by using EM algorithm.
Okay, sir. Thank you. And your lecture was very excellent, sir. Thank you, sir.
Any other?
Sir, good evening. This is Mirza from Lord's College of Engineering Technology, sir. Sir, you have shown in the compression of the image, 73% efficiency you have shown, sir. So still
Okay.
we can increase the efficiency of compression?
Definitely possible. These are all the pure stages. By using one technique only. Now
Yes, sir.
today compression is going with hybrid techniques.
Yes, sir.
Say I know to confine to one philosophy.
Okay, sir.
See what is happening? What was done in WinZip? WinZip was doing Shannai Fano encoding.
Yes, sir.
So today WinZip is not just that Shannai Fano encoding; it's something more than that. So that's the reason Shannai Fano encoding gives the compression to 1/3. So if you have a 1 unit of memory requirement, Shannai Fano gives 1/3. That is because of the second principle of entropy. Okay, but today you are able to get less than that.
Okay, so still the efficiency can be increased. You are saying that compression ratio.
It is always possible. See what is happening. If you take our days is a data.
Yes,
even
sir.
JPEG is I think Fourier coefficients. How the JPEG is stored is the Fourier coefficients of the image, is it not?
Yes, sir.
So once you have a Fourier coefficients, this becomes the data. I can apply data compression techniques on the Fourier coefficients.
Okay, sir.
So if you take JPEG alone, then it is the data of Fourier coefficients are preserved. Now Fourier coefficients are compressed as the data, then you have further compression.
Okay, sir.
So there are several this type of hierarchical or hybrid techniques are in progress now.
Okay, sir. Thank you so much.
Next, sir.
Any more? Please come forward to ask your doubts.
Okay,
sir. I think
I
there will
hope
not be any questions.
I hope the talk, though it is very elementary, ignited some thoughts for doing some research.
Yes, that too. This is the dinner time for them. 9 o'clock. No, okay. Anyway, your talk was very excellent, sir. So once again, I thank you for accepting our invitation and inspiring our FDP participants. Okay,
Fine.
we will be
Thank
in
you.
touch with you, sir. Okay,
Thank
sir.
you very much.
Yeah.
Fine. Good
So
night.
here we can we conclude the session here. Hope the participants will show the same enthusiasm and interest and participate in tomorrow's lecture. Tomorrow from Bitspilani, Thiruvikram is coming. He is a nice gentleman, and he explains the fundamentals and other transformations of image processing. Hope all the participants will join tomorrow at 7 o'clock. Thank you all.
Thank you.
once again. Yeah, thank you all, sir.
Thank you, sir.
Yeah, thank you.
For tomorrow's online session, new link will coming. So it will send to you by email and through WhatsApp group also. Kindly go through your WhatsApp group as well as the email. Thank you very much. Have a great day.